In this segment, we will study the problem of recommendation systems. The objective is to estimate the rating a user might give to a target item. We describe the problem setting in terms of graph signal processing by creating a graph where items are nodes, rating similarities between items define edges, and ratings given by users are the graph signals on top of such a graph. We will use GNNs to learn the estimated rating that a user would give to an unrated item. The use of GNNs defined on such a graph will leverage the rating similarities between items to estimate the rating of the target item based on the item the user has previously rated. In the problem setting of recommendation systems, we have items within a collection that are being rated by a pool of users. Here, we represent a collection of 11 items. Some pairs of items have been rated by multiple users, allowing us to estimate the likelihood of two items getting similar ratings, for example, by means of the Pearson correlation coefficient between items' ratings. Then, we can assume that we have a graph where items are nodes and the estimated rating similarities are the edges. Now, a user rates some of the items, which we can model as a graph signal, where we have a signal value, the rating, on top of some of the nodes. For example, nodes 1, 2, 5, 9, and 10. What we want to do in recommendation systems is to know what rating the user would give to a target item. This is the same as estimating the missing entry of a graph signal on one of the nodes. For example, node 3. We want to know what rating value xt the user would give to a target item t. We want to estimate this value based on the ratings the user has given to some of the other items, and we want to leverage the rating similarities between these items. In graph signal processing terms, we want to estimate the tth entry of the graph signal, which corresponds to the rating value xt. We want to do this based on the graph signal x, which contains the ratings the user has given to some of the other items, and we want to leverage the graph structure S that encodes the rating similarities between the items. Note that, since the user has not rated all the items in the collection, some entries of the graph signal X will be set to 0. Also note that we set the ij entry of the shift operator S to be the Pearson correlation coefficient, and then we sparsify the graph by keeping only the k nearest neighbors. We will train a GNN phi to map between the partial ratings x of some user and the estimated rating xt that the user will give to the target item t. To design the GNN, remember that we need to select the number of layers L, the number of features on each layer FL, and the number of filter taps on each layer KL. Since the output of the GNN is another graph signal, but we're only interested in the tth entry, we will include a local readout layer. This readout layer computes a local combination of features at the target node t to output xt. In other words, we take the resulting GNN output features only at the target node t and learn how to linearly combine them to obtain a single scalar that will represent the estimated rating value xt. In what follows, we will discuss the code utilized to address the recommendation system problem. First, we will discuss the creation of the corresponding dataset. In the library available in the link at the bottom of the slide, we provide tools for handling datasets. See that these tools are imported in line 1 of the code. In this example of recommendation systems, we consider the MovieLens 100K dataset that contains 100,000 ratings given by 943 users to some of the 1,582 movies available. The ratings are integers from 1 to 5. To load the dataset, the imported library has a class that is called MovieLens. We will detail how to initialize the class to create an appropriate dataset next. First, note that we want each item, or in this case each movie, to be a node. To do this, we need to specify the graph type to be movie. This will give us a graph with 1,582 nodes. Then we need to specify what is the target movie that we want to estimate the rating for. In this example, we select the movie Star Wars, whose label ID is 50. This is the movie with the largest number of available ratings. 583 users have rated the movie. Each of these users is equivalent to a different graph signals. Thus, choosing this movie gives us the largest available dataset of graph signals. We also remark that the rating given by each user to the Star Wars movie is extracted as label and zeroed out in the corresponding graph signal. This gives us a label dataset that can be used for supervised learning. Then we need to specify what's the ratio of graph signals that will form the training set and what's the ratio of the training set that will be set apart for validation. Finally, we need to specify how we're building the graph from the dataset. Edges are always computed by means of a Pearson correlation, but we get to choose how many nearest neighbors to keep. Now that we have loaded the data, we need to set the specific architecture hyperparameters. We consider a two-layer GNN architecture with 64 features as output of the first layer and 32 features as output of the second layer. All filters will have 5 filter tabs. We choose a ReLU nonlinearity. We also need to determine the shift operator S. For this, we get the graph that has already been computed by the data class that we initialized in the previous slide. Recall that this graph uses the dataset to estimate the Pearson correlation between pairs of items that ends up being the edge weights of the graph. Don't forget to normalize the graph by the largest eigenvalue. Now we are ready to create the specific architecture. For ease of exposition, we will use one of the provided architectures called a local GNN. This architecture concatenates layers of graph convolutions and pointwise nonlinearities, but also includes a final readout layer that is computed separately at each node. As we mentioned before, this readout layer just produces linear combinations of features at each node. That is, it doesn't involve any exchanges of information between nodes of the graph. So we import the architecture module and call for the local GNN in that module. First, we need to specify the graph filtering features at each layer. Note that for a two-layer GNN, we need a list of 3 elements, because the first element specifies the number of input features to the architecture as a whole. Since the graph signals in the training set contain a single scalar per node, that is the rating value, then we have only one input feature. Then we need to specify the number of filter tabs on each layer, which is k for both of our layers. Then we specify the nonlinearity, and finally the number of features in the readout layer. This is simply a local readout layer that maps the number of output features, that is 64, into the number of specified by the elements of this list, in this case 1. This will be the single scalar that we will use as the estimate of the rating of the Star Wars movie. This readout layer is performed at each node without any exchanges involved. We finalize the architecture initialization by setting the shift operator. Now that we have the specific architecture design that we will use, we need to train it. This can be conveniently done by using the model class provided in model.py. This class creates a machine learning model, that is, it binds together the architecture, the loss function, a smooth L1 loss in our case, and the chosen optimizer, an Adam optimizer with learning rate 0.005 for us. It also lets us give a name to the architecture. We note that we're trying to minimize the estimated rating with respect to the true rating, which is used as a label. We choose a smooth L1 loss because it has better gradient properties, but other choices such as the MSE are also possible. Once we have a model with all the relevant components, we can just train it by using the provided method, train. We need to specify the data class that we will use, the number of epochs, and the batch size. After training has finished, we are ready to evaluate the model. To do this, we use the evaluate method contained in the model class. This method gets the data class as the input. The output of the evaluate method is a dictionary that contains the cost, in our case the RMSE, of 2 instances of the parameters in the model. Cost best gives the RMSE of the parameters that got the lowest validation error. Cost last gives the RMSE of the parameters that we obtained in the last training step. The result of this GNN are present in this bar plot here. We see in blue that the GNN achieves an RMSE of 0.85. Even though we haven't done any cross-validation nor exhaustive search of hyperparameters, learning rates, etc., we see that the GNN still outperforms the rating estimate based on the nearest neighbor rule. This concludes the coded example of using GNNs on recommendation systems. This is just a glimpse of the library available on the link at the bottom of this slide. Please be sure to check the library for more examples as well as other pre-coded architectures ranging a wide array of alternatives including ARMANETs, node varying filters, graph attention transforms, local nonlinear activations, among many others. For those of you that are familiar with PyTorch, we point out that the library has a module that provides the basic graph operations, already coded as layer operations with the logic for handling the learnable parameters. This module follows the same functionality as the torch.nn library that provides the layer operation that can be seamlessly combined to build more complex neural network architectures. Thus, building graph neural networks becomes straightforward by combining the graph operations provided in the library.